Hello everyone, my name is Tatiana and today we are going to talk about Bitwise Operators. Our today's presenter is Danila. I hope you know them, you know him, and he is going to talk about these operators, why we use them, why we need them, and how to use them. Danila, you can start.
Uh, Thank you, Tatiana. Yeah, let's briefly discuss why do we need them. Just in short, to make you interested in them. Bitwise operators are very fast and very memory efficient. They cannot be used in all cases, but in some they can significantly improve the performance of the application. We will see an example where they improve the performance 40 times in some benchmarks. So yeah, it's quite a lot. Here is a simple task that we will be solving today. It won't be the only task, but one of them. The task is write a method that accepts a string and checks if the string contains all latent characters. The string will be lowercase only, and it will contain only latent letters. So we can write, we write this method, has all characters, and as a first implementation, we just call the naive cycle. And in this method implementation, we cycle through all the characters from A to Z, and we check if the string index of doesn't equal -1. It means, if index of equals -1, it means that the character is not in the string, and we return false. Otherwise, we return true. This code can be improved with the bitwise operators, and a bit later we will see how. Let's see that this code actually works. I have a bunch of tests. The first test is full alphabet. The second test is, the first test checks that the method returns true. The second test expects false when you pass all the characters without one letter, and the third test is a long string with duplicated letters A. We run it, and we see that the naive implementation actually works. Let's switch from this and talk about bitwise operators that exist in Java. There are 7 of them, and we'll go through them one by one. The first operator is AND. This operator accepts 2 arguments, x and y, and returns x and y. Here is a table that represents all the possible inputs and outputs of this operator. If we pass 2 zeros, then the output is 0. If we pass one argument, that is 1, and another is 0, the output is still 0. And only if we pass 2 ones, the output is 1. What should we do when we have not bits, but numbers, like integers, that are bigger than 1? We have to represent them in the binary form. So the 13 is 1101, and 6 is 0110. And then we simply go, not like that, we simply go bit by bit. The first bit, 1 and 0, according to this table, is 0. We write it to the result. The second bit, 1 and 1, is 1. Okay, 0 and 1 is 0, and 1 and 0 is 0. So the result is 0100, or just 4. I hope it's clear. And let's see 2 examples. I wrote a custom print method that just adds a bit more information. So the first example is 13 and 6. We see the same result as here in comments. The second example is like the same, but with longer numbers. So here numbers are 6 bits long. 56 and 29. And actually, here you can see that we go bit by bit to 1 and 0 is 0, 1 and 1 is 1, 0 and 1 is 0, etc. And the result is 24 because this number represents 24. You cannot really get this result using other like operators that you're usually familiar with. So it's not like plus or minus. Here results can be completely different. Okay, the second operator is OR. It requires that at least one argument equals to 1. So if we pass two zeros, the output is 0. But in all other cases, the output is 1. And if we go to integers, to longer numbers, we do exactly the same thing as we did before. We go bit by bit. So 1 or 0, it's 1. 0 or 1, 1. 0 or 0 is 0, and 1 or 1 is 1. The result of 9 or 5 is this number, in decimal is 13. Okay, let's see an example. We run it. And we see, yeah, the first example is the same as here in comments. And the second example is a bit more interesting. So we have here 10 or 2. And when we translate 10 and 2 to binary, we see that 2 has only one set bit. It's the second from right. And 10 already has this bit set. So when we do OR of these numbers, actually nothing changes because the only bit that these two could change in the first argument, it was already set. So here the result is the same as the first argument, it's 10. This property of OR operator is often used when you have to set just a single bit of the number. So for example, if we have this number 10 and we want to set the third bit to 1, we can do 10 or 4, and 4 would have set bit here, and the result would be actually 13. Okay, I hope it's at least a bit clear. Let's go further, and the next operator is exclusive OR, or how it's sometimes called, XOR. This operator requires that exactly one input argument equals to 1. So if we put inputs 2 zeros or 2 ones, the output is 0. But if we input 1 0 and 1 1, the result is 1. Yeah, as usually, we just go bit by bit. So let me, yeah, 1 XOR 0 is 1, 0 XOR 1 is 1, 0 XOR 0 and 1 XOR 1 is 0. And so the result 9 XOR 5 is 12. Okay, let's run it. And yeah, here the first example would be the same as in comments. But the second again is 10 XOR 2. Because they have the same bit set, this operator actually clears the bit of the first input 10. So what do we really say here? We say take the 10 and clear the same bits that are set in 2, or set them if they were not set. Here the bits are the same, and it actually clears the second bit, and the output is 8. This property is widely used in all kinds of encryption algorithms because using XOR, if you make a lot of XOR operations, you will not end up with a bunch of zeros or bunch of ones. For example, if you take lots of random numbers and you take an OR operator of them, you will eventually get 0. If you take a lot of random numbers and take OR operator from them, you will get a bunch of ones, and that's all. But with XOR, if you XOR different random numbers, you will get a random number. So it's used in almost all encryption algorithms. The next operator is simpler than the first four. It's not. It actually accepts only one argument, and if it's 0, it returns 1, and if it's 1, it is 1, it returns 0. So let's take the number 9. Actually, integers in Java are 32 bits long. And before I just showed the bits that mattered. And here we take 32 bits. The first 28 of them would be 0, and in the end we have 1001. And when we take not from this number, we get a bunch of ones, and in the end 0, 1, 1, 0. So I hope it's easy to understand why it's so. And actually in Java, this number means -10. We will not dig into the reasons why it works so. If you're interested, you can Google for ones complement. Here's the link. I will share the link to this code later. And there are actually pretty good reasons for doing that in programming languages. And if we run this example, we see the result is -10, and the binary result is a bunch of ones in the beginning. So the same as here in the comment. The next operator, it again accepts only one argument. Let me change the main method here. Shift left. It shifts all the bits of the input to the left. So here we have number 3. It's 0, 0, 1, 1. When we shift our bits to the left, we have these two ones set on the position 3 and 2, not on the rightmost. And the rightmost bit becomes 0. If we move, if we shift this number to the left once more, we get 2 0 bits in the end and 2 ones in the beginning. So basically, shifting the numbers to the left is the same thing as multiplying them by 2. And actually, shifting the number to the left is more performant than multiplying it by 2, but Java applies it automatically. So you don't have to rewrite all your multiplies by 2 to shifts. It would work automatically. So if we have 3 and we shift it once, we get 6, and if we shift it once more, we get 12. Let's run it, and the result is predicted, and we see that a new 0 appears to the right of our number. The shift right operator is works the same, but vice versa. It moves bits to another side, and basically it divides number by 2. So if we get a number 5 and we shift it right, we get 0, 1, 0, or just 2. If we shift it once more, we get 1, and once more we get 0. Let's run it. And we see the results. The rightmost bits of the number just disappears when we shift our initial number. And actually, Java has another operator, not 2 arrows to the right, but 3. The difference between these two operators, let me change the main method. The difference is only with negative numbers. When you have positive numbers, they behave the same, but when you have a negative number, in Java, its negativity is represented by the leftmost bit of a number. And if you use shift with 2 arrows, the operator will preserve the sign of the number. So if this bit was 1, it will be 1. and three arrows will just always put 0 here. So in negative with negative 10, let's see, the first result is with 2 arrows, and the second is with 3 arrows. Yeah, as you can see, with 2 arrows, we preserve the sign, so we divided -10 by 2, and we got -5 as expected, and the leftmost bit here is 1. And if we just use 3 arrows, we get some very big number, 2,147,000,000. It's yeah, one of the biggest possible positive integer numbers, and the leftmost bit here is 0. Okay, these are all bitwise operators that exist in Java, and now we will go through their applications, but maybe you have some questions, Tatiana?
I don't see any questions for now. I think you can proceed.
Okay, let's see one of the most default tasks that are solved with bitwise operators. The task is to determine if a number is a power of 2 or not. We can write a naive implementation here. So here we just create some integer power, it's equals to 1, and then we make a while true cycle, and if our I equals to the power, we return true. If the power is less than 0, it means that we have an overflow, we return false. If the power is bigger than our I, it means that we checked all the previous powers, and our I is not a power of 2, we return false. And in the end, we multiply the power by 2. This algorithm works fine. It's pretty fast because it has only mathematical operations, so that are extremely fast. But still, if you get a number that is like 2 to the power of, let's say, 30, you will have 30 cycles inside this while true loop. You will make these 3 comparisons 30 times, so it's 90 comparisons. It's like a lot of job to do. We can do better. For example, we can take the property that a power of 2 is always in a binary representation 1 and a bunch of trailing zeros. And if we subtract 1 from this number, if the power is number of 2, if the number is a power of 2 and we subtract 1 from it, it will be actually 0 and a bunch of leading ones. And here we can see that if we take bitwise AND between these two numbers, we will actually get 0, because no 2 bits in these numbers are set at the same time. So the property for the power of 2 is I, and I minus 1 is always a 0. For other numbers, it doesn't work. So if we get some number that is not a power of 2, subtract 1 and take bitwise AND, we will get some non-zero result. So we can use this to write an algorithm. Actually, 0 is a special case, so we have to check it separately. So our method can return I not equals to 0 and I and I minus 1 equals to 0. This algorithm has a limited number of operations. So if you pass here 2 or 2 to the power of 30, the performance of this algorithm will not change. And actually, it's so fast that it's really difficult to measure it, because like the overhead of measurement is just too big for this tiny method. Let's return to our strings tasks. Yeah, just to remind you, we have to check if the string contains all the letters from A to Z. And we can do it using a simple cycle and index of method. Can we do it better? Yes. The first, what is the problem with these methods? If you have very uh, actually, no. If you have any XYZ, if you have any string, you have to cycle through it 26 times to see if the string contains all the characters. If the string is very long and, for example, has a million of A's in the beginning, you will have to cycle through all these A's and check them independently 26 times. It's a lot of waste. What we can do? The first solution that we can implement doesn't use any bitwise operators. We, yeah, let's just count how many characters of each type did we see. We create an integer array of the size 26, so it's like the size of English alphabet, and then we cycle through all the characters in the string and we increment the corresponding integer. And in the end, we iterate through this array and we check if any of result is zero, then we didn't see this number, we return false. Otherwise, we return true. This algorithm is better in some situations. So it will have only two cycles. If you have a string with like 10 million characters, you will have to iterate through them only once. And well, yeah, the second cycle is required, but it's always small. It iterates only through the 26 characters, 26 elements in an array. That's all. But actually, this algorithm wouldn't work well if we have like ABC and all other characters, X, Y, Z, and then a bunch of A's, like 10 million. It doesn't matter. The first algorithm would see all the characters in the first 26 characters and then stop, return true, that's all. But this algorithm would have to iterate through all the characters. But okay, let's ignore it for now. Can we do better? Yes, actually, of course we can. We don't really need to count the characters. We just have to see, have to check if we saw this character or not. And what can we do it with? We can do it with booleans. So instead of creating an array of integers, we create an array of booleans. Instead of incrementing, we are setting the element to true. And instead of checking if it's equals to zero, we just check if it's true or false. The rest of the algorithm stays the same. Okay, but can we do it better? Actually, yes, we can do it with a bitwise operator. So that's actually why this example is in this slide top. We can take an integer and use it not as a number, but as a bunch of Boolean flags. So Boolean is actually, it can be true or false. We can model it with either 1, 0 or 1. And our integer, it's 32 bits long. So each bit, we can think about it as a Boolean flag. And yeah, here we have our integer result, and we iterate through all the characters in the string. And what we do, we make a result. Actually, this is the short notation for a result equals result or and some number. What is this number? This number it, will have only one set bit in the place corresponding to the corresponding to the character that we are currently seeing. So if we pass here a, it will be a minus a, it's 0. 1 moved to the left 0 times, it's 1. It will be this. Okay. I have something. Okay, it will be this number, and we will actually just set these bits in the result 1. If we pass here, for example, c, c minus a will be 2. 1 shifted left by 2 will be 4. It will be this set bit, and we will set this bit in the result. And when can we terminate the algorithm? When all the latest 26 bits of the number, it will be of the result, are ones. So when we see that our result equals to this number, it means that we saw all the latent characters in the string, and we set all the flags uh, in this number. And yeah, here we can just check if the result equals to this number. It's just a short way to write it, but actually I think you can do it. Let's check it. I haven't checked it before. You can write it like that, like just a binary number. And if the result equals to this number, you return true. If you finished it written and didn't return true, you return false. That's all. Uh, and we can compare the performance of these algorithms. I will not show you the way of running benchmarks, but I will commit them too, and you can play around with them, but they're a bit too advanced. But here are the results. If we have a string with 26 characters of the English alphabet, and we have 4 implementations: naive, cycle, array, boolean array, and bytes. Actually, this number is microseconds spent per operation, per method call. So the naive implementation is really fast. It only required 92 nanoseconds to run this method. But the bytes implementation required only 27. So it's like 3.5 times faster. And array and boolean array are twice as fast as the naive implementation. If you pass here a longer string that is like few hundred characters long, the naive implementation takes 162 nanoseconds. Boolean array starts winning integer array and significantly winning, and the bytes implementation is actually a bit faster than a Boolean array. Yeah, here don't really pay the attention to the exact numbers, just to see how they relate. Yeah, so here bytes implementation wins over all other implementations. Okay, if you have any questions about this algorithm, you can ask them. I will try to answer once more, probably. Okay, you may say, this is a cool approach. We didn't know about it, but who on earth would ever use this? This is not actually readable and it's not a good code. And for that, I have a thing to show to you. So if you remember, Java Reflection, it's a tool to access meta information about classes. So we can, yeah, here I have a class flags with some static methods. Doesn't really matter what this method does. And using reflection, we can do flex.class.getDeclared methods with name method. Okay, and we have this method. And a class method has get modifiers method. Actually, using another static utility method, we can check if our method is static. It is static, so this code should print true. Let's see what it prints. And what do we see? Method modifiers equals 10. It's not an object, it's just like 10. What does it really mean? And is static equals true. Okay, let's remove the static and check it again. And modifiers became 2, and is static returns false. So Java actually works. It doesn't return modifiers, just random number. Okay, let's see how it works. Get modifiers returns a simple integer that actually works as our result in the previous example that I showed you. This integer is thought of as a bunch of set bits. And actually, this modifier is static. What it does, it returns our modifiers and some static constant that it equals to hex value 8. So it's this one is the same as just decimal 8. And we check this, that this AND operation doesn't equal 0. So we just check here if our fourth bit in the modifiers is 1 or 0. And actually, it allows you to store data very efficiently. On most GVMs, Boolean takes 1 byte or 8 bits. Why it's so? Actually, yeah, Boolean can take 1 bit because it can be either 1 or 0, but there are other reasons for doing that. For example, if you have well, not all processors allow you to interact with single bits. They allow you to access only bytes, and that's why Java requires to get 1 byte to each Boolean. And actually, if you have to store 30, well, yeah, let's say that for method modifiers, you have to store 6 flags. If you will do it with booleans, it will be 6 bytes with booleans. With integer, it can be actually 1 byte. Integer is 4 bytes, but you can store it as a byte b, and it would be 1 byte. So you can save a lot of memory using this approach. And yeah, this memory is saved for each method that exists in your application, and it's just a lot of memory. So I hope I showed you that this approach is really used, not always, not in all cases, but sometimes it can save you a lot of memory. And I think that here we can make a short stop for the questions if you have any.
Actually, yeah, again, I don't see any questions in the chat, so if you have them, please post.
Okay, I will just think that I explain everything and that I explain everything cool and you understand everything. Okay, let's see the BeatSet. Actually, it is a standard Java class, like Java util BeatSet, that allows you to manipulate single bits in a set. Okay, so here, yeah, let me run it, and let's see how it works. BeatSet, yeah, we create a bit set, then we set a bit number 4, then we can set a bit number 10, then we can clear all the bits from 5 to 15, so it will actually clear this bit 10. We can create another set and set the bit 3, and then we can take a logical OR of these bits, output the resulting bits, and the cardinality, it's a number of set bits. If we see what it outputs that our resulting bit set contains 2 bits, 3 and 4, and the cardinality is 2. Okay, we can count it by hands. 3 is 1, 4 is 2. Okay, we have 2 set bits. This class, I actually haven't used it ever before I started preparing this light talk. But I have used something that well, resembles this class in Redis database. And let's see how it can be used in a real-life production on the user statistics example. Yeah, so it can be done with Redis database. It's like my favorite database. I always promote it when I can. And we can actually, yeah, let's imagine that we have a website with 1 million users. And these users log in to our site. And we want to see how many of them logged in today, yesterday, the day before yesterday, etc. And then we would like to see how many of them logged in every day this week, or who logged in only once this week. And this can actually be very efficiently implemented with BitSet or like similar bit operations. Yeah, here I have a BitSet MondayStatistics. It's like just returns random statistics, how it is gathered. We create a BitSet with a million of allocated bits. It's actually not a lot. 1 million allocated bits is something around 125 kilobytes. In modern system, it's like nothing. And still, it stores the information about users logged in the whole day if you have million of users. And then I simulate 100,000 random events, for example, logins. We just generate a random number from 0 to million, and we set the corresponding bit, and we return the bit set. So we get a random statistics for Monday, random statistics for Tuesday, and actually, what can we see here? We can see the first number will be how many people logged in on Monday. It will be Monday.cardinality. It's 95,130. Other 4,000 blah blah logged in twice. So that's why it's not strictly 100,000. Then we can calculate how many people logged in on Monday or Tuesday. We just take logical OR and output the cardinality. It will be 181,000. Okay, and how many of them logged in on both days? We just change this OR to AND. We rerun this application, and we see that only 9,000 people logged in on both days. Yeah, again, this can be very efficient in terms of memory and CPU. If you have, I don't know, 100 million users, it's like a gigantic website, a gigantic system, you would need only something around 12 megabytes to store information for the day. Yeah, this approach can be used in the real life applications. It's limited in the sense that you just track if some event happened or not. So you don't count how many times a user logged in per day. You cannot calculate the time when the user logged in, for example, to see that everyone logs in at 8 a.m. or everyone logs in at 6 p.m. These statistics pretty limited, but it can be powerful just because the space it requires, and you can gather, for example, 100 different statistics, and it still would be very efficient. And yeah, actually using the BeatSet, we can implement our strings example. So instead of setting a bit in the integer, we set a bit in the BitSet and check the cardinality if it equals to 26. We return true or return false. But BitSet, from what I saw while preparing this slide talk, it has quite a big overhead comparing to the usual integers. So this approach works much slower than this bytes approach, but the huge benefit of the BitSet is that it can grow automatically. So the integer is limited to the 32 bits and BitSet is not. And the last example that I have for today, yeah, you have time to ask your questions if you have any. We have the task write a method that accepts an integer array and returns a single number that occurs in this array odd number of times. Yeah, we can actually see the tests for this method. Yeah, let's see this one. We have an array, and let's count fives in this array. We have two fives. It's even number of times. Okay. Fours, yeah, we have two fours. Okay, and two ones, and only one three. So here we return number three because it occurs odd or one number of times. And with a longer array, it's like the same, but three occurs five times, not one, but it's still odd. So we again return three. Okay, how can we implement this task? The first is using some map. It would probably be the first code that I write. What we do, we create a result hash map from integer to integer, and then we just go through all the numbers of array and count how many did we see. Oh my god, each of them. These compute methods, yeah, it actually has very big documentation. It's a fancy method that allows you to pass lambda here, but actually what it does, if we have I in map, increment the counter. Otherwise, store 1. If you're not familiar with this method, better take a look. It's pretty popular. And there are other actually computer fabs and computer present. But yeah, okay, let's not dig into it right now. Then after we counted all the numbers in the array, we go through all the entries and see if the counter is odd, then we return the number. Otherwise, we just throw some exception, but we don't really care about it. This algorithm works okay. Recalling the previous light talk on streams, we can rewrite it with a stream. We create a stream from this array, we box it to have not int stream, but stream from integers. Then we collect it grouping by the number and counting, and in the end we will have map of integer to long with the count of these numbers. Then we take entry set of this map, then we again take a stream, filter by the counter is odd, find any and get key, otherwise throw an exception. This algorithm works too. It's, I think, shorter. Readability is dubious, but still it works. But what can we do with bitwise operators? I think I have already spoiled it, that we will use XOR here. We rely on property that I XOR I equals 0, because all the set bits will be, well, the same bits set in the number if we XOR it with itself. From this property, I XOR I XOR I XOR I even number of times, it always equals to 0. And if we do it odd number of times, we will have, as a result, I. And just to implement the required algorithm, we take some result 0, and iterating through the array, we make result equals result XOR I. And that's all, we return results. Okay, this algorithm can be quite difficult to grasp immediately, but you can play around with this code. Again, I will leave a link a bit later. And yeah, you can actually see that it works. Okay, it's much shorter. It's like 5 lines instead of 10 lines. What about performance? Let's see. Let's first compare map and stream. Actually, stream is much slower than map. I'm not sure why. Well, definitely stream has some overhead, but I think also an important role plays the fact that here the counter is long, and here the counter in map, the counter is integer. I think it may influence the performance, but I'm not that sure. Okay, so we see the numbers. Yeah, actually the array index. Let me show you how the benchmark looks. Yeah, depending on the index of the array, that doesn't really mean anything. We give different arrays to our algorithm. So the first array is pretty short, the second is longer, and the third one is even longer. And we compare these three these three arrays. And yeah, if we compare it with the XOR implementation, we see that for small arrays, XOR is 19 times faster. With an average array, it's like 32 times faster, and with the longest array, it's like 40 times faster. The numbers themselves don't really mean much, but you can see how much does it influence. And maybe if you have an array with million of elements, actually XOR implementation can be 100 times faster. It's like, yeah, even here you win almost, well, 40 times. It's really a lot by writing a simpler code, and you can write this code if you understand some property of binary operations. Okay, I hope it was useful for you. That's it from my side, guys. Any questions?
Yeah, I think everything was clear and no one has any questions.
Okay, got it. The link to the code will be in the description of this video. I think I will post it soon, maybe in an hour. Uh, yeah, thanks,
Yeah,
guys,
thank
for
you.
joining us today.
Yeah, thank you for joining and yeah, see you next week.